Welcome to part 2 of the 5-part series on the ASHRAE Standard 90.1-2010. If you haven't seen the full list of the parts that we're planning to present, you should watch part 1 to get the total overview of all the presentations. I'm Larry Degelman, presenting again for the Energy Systems Lab at Texas A&M. And we want to acknowledge our sponsors of this series, the ARRA, the U.S. Department of Energy, and the Texas State Energy Conservation Office, SECO. This particular series this part will emphasize only the walls, roofs, and fenestration provisions of the standard. In the standard itself, this is labeled as Section 5. So we're going to devote this totally to Section 5 envelope. Each space is included in a category. It's either non-residential conditioned space, or it's residential conditioned space, or it's semi-heated space. A lot of people think that we shouldn't be talking about residential spaces because ASHRAE Standard is for commercial buildings. However, ASHRAE does apply to high-rise residential, so that's why we do include here residential spaces. Another note, spaces are actually assumed to be conditioned at the time of construction, regardless of whether there is an air conditioner present in the building permit application or whether one's installed in the building already. As far as denoting spaces as semi-heated or unconditioned, in climate zones 3 through 8, these are only permitted if it's approved by the local building official. Please make another note that only climate zones 2 through 4 apply to the Texas locations. This is showing the format generally for every one of the compliance sections. We begin up here with the mandatory provisions. That's subsection 4. So in this case, it's section 5.4. We can go straight to a prescriptive option, 5.5, and then on to compliance. As an alternative to that, we can choose to go to a trade-off option, which is 5.6, and then on to compliance. So there's always a couple different routes that you can follow to get on to complying with the code. This slide shows the space definitions. Basically, you'll see dark red surfaces here that separate the conditioned space from the outdoor or a conditioned space from a ventilated attic. Those are denoted as exterior envelopes. What's shown in gray is called a semi-exterior envelope, and that separates conditioned space from a semi-heated space or a semi-heated space from the outdoors. So there's a more lax requirement for insulation values when you go to the semi-exterior envelopes compared to the exterior envelopes. In section 5.4, again, this is mandatory. The building is required to have a continuous air barrier. A lot of people refer to this as a house wrap. The entire building's to be designed and constructed with that continuous air barrier. Specific numbers on that is that the individual materials have to have a permeance of only 0.004 CFM per square foot. And if you use assemblies, they can have an average air leakage rate of 0.04 CFM per square foot. Now, concrete masonry walls are permitted, but they need to be fully grouted or painted. That means something more than the typical mortar joint. In other words, the grout is a much finer concrete mix, and it prohibits a lot of air infiltration. So that either has to be grouted or painted. On the air barrier design, it has to have the components on the plans have to be clearly identified and noted on all the construction documents. The joints and the interconnections and penetrations of air components, air barrier components, this includes light fixtures and so on. They have to be detailed also. The continuous air barrier has to extend over all the surfaces of the building, completely from the lowest floor up to the exterior walls and the ceiling or the rooftop. Continuous air barrier has to be designed to resist positive and negative pressures from the wind, and also from the stack effect that you get in the building, and from the mechanical ventilation, which also creates internal air pressures. As far as installing the air barrier, all the joints around windows and doors have to be sealed. The junctions between the walls and foundations, openings at penetrations of walls, roofs, and floors. If you have site-built fenestration, doors and so on, that has to be caulked and weather stripped. Building assemblies used as air ducts or plenums, those have to be sealed. Any other penetration that occurs through the vapor barrier in the wall or plenums, any other opening in the building envelope has to be sealed. Here we have exceptions, and these will occur frequently throughout. Semi-heated spaces are accepted in climate zones 1 through 6. The single-wide concrete masonry building in climate zone 2B is also exempt. That happens to be the climate zone that includes Laredo and Del Rio in Texas. This shows air leakage requirements for fenestrations and doors. Specifically, this is the NFRC, National Fenestration Rating Council, test method 400 for leakage in windows and doors. And you can see this label over here at the right, that should appear on all the windows. That should be provided by the manufacturer. And just to pick a few numbers off of here, this first number is the thermal U factor, that is the conductance of heat through the window. This one's shown as 0.35, just as an example. And the next number is the solar heat gain coefficient. That's the fraction of solar heat that actually gets through the window. This number here, 0.51, is the amount of daylight transmissivity. They call it visible transmittance. So you want this visible transmittance to be actually greater than the thermal transmittance. That way the window is not a detriment for heat gain, heat loss, but it's a benefit from the daylighting viewpoint. That is admitting of outdoor daylight. This is an air leakage rate over here. So all of these numbers are shown on the manufacturer's labels. And what the ASHRAE code then limits you to is 1 CFM per square foot if you have a swinging entrance door or revolving door. If you have curtain wall construction, it's limited to 0.06 CFM per square foot. Skylights allow a much higher rate, 0.3 CFM per square foot. Now the non-swinging doors allow 0.4 CFM per square foot. And any other products, such as the one shown over here, actually 0.2 CFM per square foot. The exceptions to this are field fabricated fenestration and doors, or also metal garage roller doors in semi-heated spaces, but this is only in climate zones 1 through 6. In the case of loading docks, this is required in climate zones 4 through 8. So we do have some of the requirement in Texas, that is up at in the Panhandle. This applies to cargo doors and loading dock doors. They have to be equipped with Weatherseals that kind of close around the back end of a trailer truck as it backs up to the door. This prevents air infiltration when vehicles are parked in the doorway and then the doorway is opened. Air leakage in vestibules. This is section 5434. This is required in all building entrances in climate zone 3 for entrances in a 3-story building or a building of greater than 10,000 square feet. So, not required, down here you can see in the exceptions, it's not required in climate zones 1 and 2. It's also required in climate zones 4 through 8 in much smaller buildings. That is, those buildings only have to be 1,000 square feet or more. And those vestibules must have a self-closing door. They have to have interior and exterior doors that won't open at the same time, and that the distance between the interior and exterior doors cannot exceed 7 feet when they're in a closed position. We have a note here to remember ADA. ADA requirements, American Disabilities Act, requires a certain turning radius for wheelchairs, so that has to be also taken into consideration, though it's not an energy concern per se. On the building envelope, we're going to talk now about the window-wall ratio. That's percent glazing in the walls. This has to be equal to or less than 40% of the gross wall area. The skylight roof ratio has to be less than 5, or equal to or less than 5% of the roof area. And the envelope component must separately meet the requirements in tables 5.5. Now, 5.5 is not visible on this slide. I'm going to show you that here in a minute. There are 8 criteria sets for the different climate zones. That is, there's one table for each of the climate zones. And on those tables, you're going to see all the prescriptive requirements for the insulation level for the roofs, walls, and the floors. And we're going to see the window fenestration area requirements. You can also, as an alternative, you can use the trade-off option, which is described in section 5.6 of this particular section. Or you can go to the energy cost budget method, which is clear back in section 11 of the standard. Okay, this is what the roof view factor requirements are in Texas. I point out here that there have really been no changes since 2007, but fairly significant changes since version 2004. And I thought I'd just highlight some of these with some of the cities in the state shown over here. And over here in kind of a maroon color, you can see some of the values that have been changed, and of course they're changed in the downward direction, meaning the requirement has gotten more stringent, between moving from 2004 up to 2010. So here, for example, we have a U factor of 0.027 right now for a non-residential building, and that is for the roof. And back in 2004, that requirement was 0.034. So basically, you were restricting the heat loss through the roofing materials to a higher extent than it was in the earlier version. So there has been increased stringency, as you can see. And down here in the Dallas-Fort Worth area, in this climate zone 3, you can see there are also changes there. And again, they went in the downward direction. And the climate zone 4 includes Amarillo. You can see maybe 5 different changes right there. So that's represents an increased stringency, and that's the tendency of the standard, and that is to keep adding more stringency and presumably using less energy than the version before. Let's look at details of these tables. I mentioned earlier these are all in table 5.5. So each table will say 5.5, and then it'll have a dash and then a number, and that number is the climate zone. So this is the table of requirements for climate zone number 2. And this is only the opaque elements. So what I'm showing you here is the upper half of the table. And let me go down the left side. These are the elements. You're going to talk about the roof. Here's the wall section. Here are the walls below grade. These were walls above grade. Here, requirements for the floors. Here's slab on grade. And here, requirements for the opaque doors. Over in this direction, you'll see divisions for non-residential, residential, and then semi-heated spaces. And then in the columns in those, you're going to find an assembly maximum U value. U is the conductivity or the conductance of the overall wall assembly. That's in BTUs per hour per square foot. Right next to that, you'll see an R value. And most people are used to seeing R values as indicators of the insulation level on the rolls of insulation. So in between the joists, we have the R values, and so you would have to meet that requirement. Or if you do an overall U factor calculation of the roof or wall, you'd have to meet this number here. So in some cases, the U value is not the exact reciprocal of the R value. And the reason for that is because of the joists that are involved in the space. When you see this CI, that means continuous insulation. So for insulation entirely above the roof deck, you're thinking of a continuous polyisocyanurate styrofoam type insulation that goes over the whole roof. So that's why you see the CI there, and sometimes you'll see that on the walls. As an example, what they call a mass wall here, that's concrete blocks or concrete walls. And a lot of times the insulation is simply glued onto the wall, so you'll see the CI there. Let's see, down here on the floor slabs you'll see a thing called F. F is similar to a U factor, but it's conductance per lineal foot and not per square foot. So you're seeing here the requirement, the limiting requirement for the BTUs per lineal foot of slab edge. When you see a C, like here on the basement walls, that's the conductance of the wall in BTUs per hour per square foot, but it does not include any air film coefficient. Logically, because there's really no air film on the outside of a basement wall. It's simply adjoining the earth at that point. ASHRAE in their user's manual tries to help you identify with what they're talking about when they talk about different wall assemblies and roof assemblies. So they have pictures here showing what's the definition of a roof when your insulation's entirely above deck. They show what they mean by metal buildings, and here by what they're talking about when they refer to attic and other kind of spaces. They do a similar thing with the walls. These are mass walls, as I mentioned earlier. This is concrete block or concretes. You could have solid bricks and so on, as long as it meets their mass requirement, their mass definition. Metal buildings, again, steel-framed buildings, and then finally wood-framed buildings. So again, these are pictures that help the user to identify with what they're talking about when they use these element statements within the tables. This is a definition of what's called a mass wall. And to define a mass wall, you have to look at its heat capacitance. They call that HC, and that is BTUs per square foot per degree Fahrenheit. Not BTUs per hour, however. That would be a U factor. BTUs per square foot per degree Fahrenheit is a way to talk about the thermal capacitance of the wall. That is, how many BTUs could the wall store per square foot per degree Fahrenheit of temperature rise. So the way they do this is they take the weight of the wall. This is pounds per square foot. That's like if you cut a square foot section through the wall. And how many pounds would that be? That's that number right there. What fraction of the wall it covers, the specific heat, you have to obtain that number from maybe the ASHRAE Handbook of Fundamentals or elsewhere. That's BTUs per pound per degree Fahrenheit. And then multiply those three together, and that gives you the thermal capacitance, the heat capacitance, HC. take those layers. In this example, they show concrete block, they show wood studs, they show R11 bat insulation. Here's a piece of sheetrock or gypsum board. Add those together and you'll find this example number I'm circling here with the cursor is 10.8. That's the thermal capacitance of that wall. So the criterion to define a mass wall is if that heat capacitance is greater than 7, then it is called a mass wall. And that's for high density materials. If your wall happens to have light density materials, such as straw bale walls or something like adobe, something like that, lightweight materials, if they're that criterion is only 5, so that particular lightweight wall would have to have a heat capacitance of 5. And in the table then that gives you a certain leniency based on whether it's a mass wall or not. There's another section here on cool roofs. This is required in climate zones 1 through 3, so we're talking most of Texas to be sure. The requirement here is that on your roof, you have to have a 3-year aged roof reflectance of 0.55 or greater and an emittance of 0.75 or greater. And that has to be labeled and certified by an ASTM test. The other option to that is you can have a 3-year aged SRI. They call that the Solar Reflectance Index. And that has to be 64 or more, and again it's certified by a certain ASTM test. Third alternative, you can have increased roof insulation based on one of another table that's in the standard, table 55312. Here's an approximation equation to derive an SRI. This is not exact to be sure. This is just an approximation. The SRI is around 100 times a quantity, the reflectivity plus 0.12 times the emissivity. And I show you a table here on the right. This is what you would need in emittance and reflectances, these combinations, to give you that SRI of 64. Again, I emphasize the word approximate here, but somewhere in this neighborhood would be the number that you would need if you want to reach the SRI of 64. The requirement that I mentioned earlier is the one here on the bottom. You have to have an emittance of 0.75 and a reflectance of 0.55. So if your emittance is less, going up the chart here, then your reflectance has to be a little greater to reach that point. And again, that has to be a number as tested by the ASTM E1980. This is the third criterion for the cool roof. If you can't meet the SRI requirement or the reflectivity, emissivity requirement, then you can use this table. Again, showing you this is only climate zones 1 through 3 for all the opaque elements on the roof. You look at the assembly maximum U value for non-residential and residential. So if your insulation's entirely above the roof deck, it's 0.03. If it's a metal building, it's 0.028. So a very simple requirement, and it's only in one simple table like this. You could also just look at the R value. That is, you have to have an R33 if your insulation's all above the roof deck. And if you have a metal building, it has to be R35. Residential is R34. And there are exceptions to this as well as many, many other things in the standard. So here are the exceptions to the cool roof. If you have a stone ballasted roof weighing 17 pounds per square foot or more, if you have a vegetated roof, some people just call that roof gardens, with 2.5 inches of soil on it. If that covers 75% of the roof area, then you're growing plants and so on, then that's exempt. If your roof is shaded, that is 75% of it's shaded on June 21st by permanent features. If your roof is covered by solar collectors or solar PV arrays, things like that. Any combinations of those would be exempt. If your roof is steep, and their definition of a steep roof is 2 and 12, as shown right here, that's exempt. Or if you have a low-sloped roof in climate zones 2 and 3 and it's a metal building, that's also exempt. If your roof is over a ventilated attic or a semi-heated space, that would be exempt. If you're using asphaltic membranes in climate zones 2 and 3, those are exempt. Now this is the lower half of that table. Table 5.5 again, -2, that's for the Houston, Austin area. This is for fenestration. Some people call them windows. ASHRAE prefers to use the word fenestration, meaning all glazing. So that can include glass in doors and things like that. The first requirement is that it's less than or equal to 40% of the entire wall area. So as you can see here, the windows are restricted by U value. That's the thermal conductance through the window. And they're restricted by a solar heat gain coefficient. That's, again, that's the percent solar radiation that's allowed to pass through the glass. And we have a breakdown into vertical glazing, and that could have non-metal framing or metal framing or entrance doors and so on. That makes a little difference in the U factor requirements that are shown over here in the column. Skylights are shown separately. They have their own requirement depending on what percentage of the roof area they cover. They have different requirements if you're only using up to 2% skylight area, and a more restrictive requirement if it's between 2 and 5%. 5% is always the total maximum coverage of the roof that you're allowed to have. So the variations in U factor requirements are based on whether the skylight has a curb or whether it does not, whether it's plastic or whether it's glass. Again, this is just like the opaque section. Different numbers are restricted for non-residential, residential, and semi-heated. Okay, that covers the actual requirement for the window. Now, how do you know your solar heat gain coefficient? You have to obtain that from a rating that's determined in accordance with the National Fenestration Rating Council, and that's their test method 200. And in lieu of that, some years ago we used to always be told that windows have a shading coefficient. And that was available from NFRC. That was their tested method 300. They determined the shading coefficient. And that was the percent solar radiation penetrating a window, but compared only to a single pane glass. If you don't happen to have the solar heat gain coefficient available to you from that NFRC test, you can take the shading coefficient, and again, that's from another NFRC test, 300, multiply that by 0.86, and what the ASHRAE standard is saying here is that that is acceptable as the determination of your solar heat gain coefficient. The solar heat gain coefficient can be used as the center of glass number that's specified by NFRC 300. Let's say you don't have either one of those available to you. That is, the label is not on the window or the skylight. You can go back to the Appendix A in the standard, and this happens to be Table A 8.1. You can get the solar heat gain coefficient there for skylights, and then for vertical windows you can use Table 8.2. And this is called a mandatory appendix So you do have to use this if you do not have the manufacturer's rating that's labeled on the glazing. Those solar heat gain coefficients can be adjusted. If you have overhangs, you're going to get credit for those. You can reduce the solar heat gain coefficient of your glazing. That is, you're claiming it's reduced by using a overhang number that's in the next table that I'm going to show you here in a minute. And another exception to all this is if you're on the street side of a building at the street level, and if that story height is less than 20 feet, and if you have an overhang that's 50% of the height of the glazing, you're allowed to have your window-wall ratio go up to 0.75, and therefore this is the one place you're not restricted to that 40% requirement that I showed you earlier. Notice there are no solar heat gain coefficient requirements for semi-heated spaces in any climate zone, nor is there a requirement for residential buildings in the far north climates, zone 7 and 8. This is where we talk about the credit you'll get for external shading. It's limited to overhangs, however. It's not provided for external shading devices such as vertical fins or non-permanent devices like awnings and so on. Shading effects from geometry of some other devices, slatted louvers and screens, they may be converted to equivalent overhangs, but that has to have the approval of the building official. Okay, here's the specific of that. Your credit is given for the permanent overhang by using this adjustment in the table. First of all, look at the geometry of the overhang versus the window. The overhang dimension is measured from the glass out to the bottom edge of the overhang. That is the outer edge, I should say. And the vertical dimension, B, is measured from the window sill up to the lower edge of the overhang. So divide A over B, and that's called the projection factor, PF. Go into this table. Look at the projection factor number here. You can move over here and find your solar heat gain multiplier for all the orientations except north, and then the next column is the multiplier you use on the north wall. So you can see some of these numbers. For example, if your roof overhang is 50%, that is 0.5, you'll be able to adjust your solar heat gain coefficient downward by as much as 0.61. So a fairly significant reduction there. This is the stipulation on the street side requirement, or I should say it's really the exemption. This allows you to go up to 75% glazing, obviously for merchandisers trying to show their products to street passersby, looking through their window fronts, their store fronts. So again, if you're on the street level, this height is less than 20 feet here. Your projection overhang is 50%. You can get away with 75% glazing. Okay? Some of these slotted diffusers, or not diffusers, slotted sunshades can also be regarded as acceptable for this exemption if it blocks out the sun totally on June 21st. That's the main requirement there. I threw here a couple, maybe three equations for sun angle calculations at noon. Of course, this is only used on south-facing windows. You know, on March 21st and September 21st, we call that the equinox. The sun angle is always at 90 minus your latitude. Very simple. Just 90 minus your latitude, that gives you the sun angle at noon. And in the summer, June 21st, you add 23.5 degrees to that. And in the winter, December 21st, just subtract the same amount. So this will give you your sun angles throughout the certain seasons of the year. And yet another requirement on the fenestration orientation related to the window areas. What this is telling you is that the area of the window on the south, that's AS, has to be greater than or equal to the area of window on the west, AW. And also, the south glazing has to be greater than or equal to the window area on the east wall. And there are certain stipulations here on what's considered east. Well, what's considered east is anything that actually looks east but plus or minus 45 degrees. And what's looking south has a similar dimension to it of deviation from due south and due east and due west. So anyway, these are all outlined here in this section. And if you get a hold of the ASHRAE manual, you can look that up at 55.4.5. And here we see that skylights are actually required in certain cases. They are required in enclosed spaces that 4 stories or less. It's 5,000 square feet or more, and directly under a roof with ceiling height greater than 15 feet. This applies to any of these kind of spaces that are listed here, and you can read them: office, lobby, atrium, concourse, and so on. The specific requirements of this are that the daylight area under the skylights has to be equal to or greater than half of the floor area, and either the skylight area to the daylit area ratio is greater than 3% when the glazing visible transmittance is greater than 0.4, or the skylight effective aperture area is greater than 1%. The effective aperture area is 0.75 times the skylight area times visible transmittance times a well factor divided by the daylight area. That's their definition of effective aperture area. Visible transmittance we've mentioned earlier. The well factor is a new term here. It simply lowers the amount of light that gets into the space due to the size of this well that's at the base of the skylight. So the depth of the well will affect it. If it's greater than 2 feet, then that well factor is 0.7. If it's less than 2 feet, then the well factor is 0.9, so a lot more of the light would get through. There are exemptions to the skylight requirement. First of all, it's exempted in the northern zones 6 through 8. If you have a very low lighting level requirement, that's this number here, LPD, in the space of 0.5 watts per square foot or less. If your space already is blocked from receiving sunlight on at least half of the roof for 1,500 hours per year, that would be exempt. If your area under rooftop monitors greater than 50% of the floor area, and also in spaces where 90% of the skylight area is shaded on June 21st. This other requirement down here has to do with reductions in that are affected by what they call side-lighted area. And that'll be defined a little more detail later, but that has to do with the vertical daylighting from the windows. On the solar heat gain coefficient of skylights, that requirement's exempt if your glazing material has a haze value of 90% when tested by the ASTM test method. Also, if it has a skylight visible transmittance greater than 0.4, and all the general lighting in the area is controlled by photocells. This haze value that's restricted to 90% here has to do with the milkiness or the opaqueness, I guess you would say, of the glazing material on the skylight. So the more the better in this case. This is a requirement on how the insulation's to be installed. And to sum up this quickly, the picture here shows insulation in the attic being pushed up near the wall edge. And the main requirement is simply to make sure that that insulation does not block off this natural ventilation that comes in the soffit vent and goes up the roof and out the ridge vent. Blocking has to be put in there to prevent that insulation from being pushed clear to the edge. I want to cover a few alteration exceptions related only to the envelope. If you're putting storm windows over existing windows, those are exempt. If you're replacing windows, make sure the U factor and the shading solar heat gain coefficient is not greater than what was in there before. The only requirement is that it be equal to or less. If you're replacing less than 25% of the windows, also that's exempt if the U factor and solar heat gain coefficients are not exceeded. If your insulation cavity already has R3 per inch, or it's simply inaccessible, roof membranes below the roof insulation, those are exempt. If you have a vestibule, that requirement's not imposed on door replacements, but if you have an existing vestibule, you shall not remove it. That's a basic requirement there. In the building envelope trade-off option, this goes back to section 5.6. This allows you to trade off if you somehow exceed some of the U value requirements that are in the insulation tables. So you basically calculate an envelope performance factor, EPF, and the procedures for that are shown in Appendix C. And if your EPF is less than the EPF of another building that would actually meet the prescriptive requirements, then you would pass this test here, and that would be your basic trade-off. I want to mention what's in these appendices. In Normative Appendix A, we have all the skylight U factors for walls, windows, floors, and so on. And these are the numbers that have to be used if the manufacturer does not have the label on the product. So you have to use all of these values for your thermal insulation. Okay, this concludes the Part 2 on the envelope provisions, which is in the standard, Section 5. And the next section coming up will be Section 6 on the HVAC requirements. Thank you very much.